Sun are powered by fusion reactions, in which hydrogen nuclei are combined to form helium. By the 1950s, scientists had begun to contemplate how that process might be used by humanity to generate abundant amounts of energy. Nuclear reactors use nuclear fission to generate power. In nuclear fission, you get energy from splitting one atom into two atoms. In a conventional nuclear reactor, high-energy neutrons split heavy atoms of uranium, yielding large amounts of energy. In nuclear fusion, you get energy when two atoms join together to form one. In a fusion reactor, hydrogen atoms come together to form helium atoms, neutrons, and vast amounts of energy. It's the same type of reaction that powers hydrogen bombs and the sun. This would be a cleaner, safer, more efficient, and more abundant source of power than nuclear fission. There are several types of fusion reactions. Most involve the isotopes of hydrogen, called deuterium and tritium. Proton-proton chain. This sequence is the predominant fusion reaction scheme used by stars such as the Sun. Two pairs of protons form to make two deuterium atoms. Each deuterium atom combines with a proton to form a helium-3 atom. These reactions produce high-energy particles, protons, electrons, neutrinos, positrons, and radiation light, gamma rays. Conceptually, harnessing nuclear fusion in a reactor is a no-brainer. But it has been extremely difficult for scientists to come up with a controllable, non-destructive way of doing it. To understand why, we need to look at the necessary conditions for nuclear fusion. When hydrogen atoms fuse, the nuclei must come together. However, the protons in each nucleus will tend to repel each other because they have the same charge, positive. If you've ever tried to place two magnets together and felt them push apart from each other, you've experienced this principle firsthand. To achieve fusion, you need to create special conditions to overcome this tendency. Here are the conditions that make fusion possible. High temperature gives the hydrogen atoms enough energy to overcome the electrical repulsion between the protons. Fusion requires temperatures of about 100 million Kelvin, approximately 6 times hotter than the Sun's core. At these temperatures, hydrogen is a plasma, not a gas. Plasma is a high-energy state of matter in which all the electrons are stripped from atoms and move freely about. The Sun achieves these temperatures by its large mass and the force of gravity compressing this mass in the core. We must use energy from microwaves, lasers, and ion particles to achieve these temperatures. High pressure squeezes the hydrogen atoms together. They must be within 1 × 10⁻⁵ meters of each other to fuse. The Sun uses its mass and the force of gravity to squeeze hydrogen atoms together in its core. We must squeeze hydrogen atoms together by using intense magnetic fields, powerful lasers, or ion beams. There are two ways to achieve the temperatures and pressures necessary for hydrogen fusion to take place. Magnetic confinement uses magnetic and electric fields to heat and squeeze the hydrogen plasma. The IDER project in France is using this method. Inertial confinement uses laser beams or ion beams to squeeze and heat the hydrogen plasma. Scientists are studying this experimental approach at the National Ignition Facility of Lawrence Livermore Laboratory in the United States. In this video, we look at magnetic confinement. Here's how it would work. Microwaves, electricity, and neutral particle beams from accelerators heat a stream of hydrogen gas. This heating turns the gas into plasma. This plasma gets squeezed by superconducting magnets, thereby allowing fusion to occur. The most efficient shape for the magnetically confined plasma is a donut-shaped toroid. A reactor of this shape is called a tokamak. The main application for fusion is in making electricity. Nuclear fusion can provide a safe, clean energy source for future generations with several advantages over current fission reactors.